Hello everyone, welcome to this advanced reinforced concrete design. And now we are entering into the important chapter which is on columns. We are going to talk about uh, column behavior and design in 5 parts. In this part of this video, we are going to discuss about how do we classify the columns, and a very important classification of a column is to whether to design the column as a slender column or a short column. So for that, we will be using effective length. Uh, so we will talk about that. Then part two, we are going to talk about what are the code provisions that exist in IS 456 and how to understand the behavior of short axially loaded columns. We will talk about what is confinement and how is it going to influence the behavior. And part three, we are going to talk about how to analyze and design columns which are subjected to combined axial compression and bending loads. Then part four, we will move on to how to design the columns for biaxial bending along with axial compression. Then part five would be about how to design for slender columns. So how do you consider the slenderness aspects in design of columns? So these are the 5 parts that we are going to discuss in this module. Right, so we'll get into this first part of the module. Here again, as discussed, we are going to talk about what are the different column types and what are effective length. Right, so what are the expected learning outcomes? After going through this part of the um, video, the student should be able to define what is a column and should be able to also approximately, let's say for a residential building, how to calculate approximately what is the axial compression load that comes onto the columns, then how the columns are classified based on the shape, length, and the loading applications. And the student should also be able to explain what is the difference between short column and slender column. Then we'll get into the concept of effective length, how to define effective length, how to calculate effective length, all these things that we will talk about it here. And then also the student should be able to distinguish what is a sway frame and what is a non-sway frame. Then to distinguish whether the column is part of sway frame or non-sway frame, what we do is we calculate something called stability index. We'll talk about that. And then using that again, we can also do some example on calculating effective length of the columns. Right. So, and you all know that I think we have discussed this multiple times. Columns are very important load bearing elements. In fact, the collapse of column can lead to the complete collapse of a building, right? So, it is not going to lead to a localized failure. It can lead to a global failure. So, that is the reason for column design, we need to have consider more factor of safety in our design. Right. So the columns are actually the vertical compression members. Predominantly, they are compression members, and of a structural frame, as you can see, and that is intended to support load carrying beams. So, for example, in a typical building like what we are seeing here, we actually apply for gravity loads. We apply the loads on the slabs, right? Then from the slabs, the load get transferred to beams, then from beams to columns, then columns to foundation, then foundation to soil. Finally, we have to transfer all the applied external loads to soil, and then again, the safe bearing capacity of the soil should not be exceeded. Now, you can see here the columns transmit loads from upper floors to lower floors, then to soil through foundation. So, we've seen this load path. Understanding the load path is very, very important. Now, let's look at this. So, this is what we're looking at it. If you're looking at this elevation, then you can see the load path. These are your external loads that gets applied on the slab, then the transfers to beam to the column, and so on. So depending upon which floor level that you are there, whether you are here or here or here, your axial compression loads are going to change. In addition to that, this is we are talking only for gravity loads. In addition to that, you will have lateral load that is coming from wind load or earthquake. That again column which is part of the moment resisting frame that is going to take the load resistance for the applied lateral loads as well. Now let's see. So what is the definition of a column? A structural element with a ratio of height to least lateral dimension. So that means a column can have, if it is a rectangular column, you can have depth and breadth of the column. But if you take the least lateral dimension and height divided by that least lateral dimension, if it is exceeding 3, then we call them as uh, compressive load. They are defined as columns. Otherwise, it's called as a pedestal. It's a stub column, or it's a very short column with the height to the least lateral dimension is 3. Then we call them as pedestal as per the IS 456 provision. The pedestals are predominantly compression loads, but columns can have compression and bending. So usually the columns carry bending moment as well. Okay, the bending moment can act about either one axis or two axes. Okay, so that we know. So basically, if you look at this as the cross section shape of your column, right? So it can bend about this axis and it can bend about this axis as well, right? So you can have bending moment about both axes, and whatever the axis that crosses through the larger length of the section, that we call that as the major bending axis. The one that is cutting through the shorter dimension of the cross section, we call that as the minor bending axis, right? And usually in bending, the main reinforcement in columns is longitudinal, because longitudinal bending creates normal stress, right? So the bending, uh, the longitudinal reinforcement is going to carry the tension that is coming from your bending. And in addition, we have also discussed in the chapter on axial behavior, for columns under pure axial compressions, you know that the major load contribution comes from concrete only, and steel we provide 2%, 3%, or max 4%. Generally we don't provide more than 4% of reinforcement in the columns. So the majority of the load resistance in pure compression comes from concrete. However, in bending, we have done the moment curvature analysis. Columns are actually, if you look at it, when it is subjected to pure bending, they have reinforcement on the compression side as well as on the tension side. In fact, usually columns will have symmetrical reinforcement. So because you have same area of steel on compression and tension, in pure bending, such sections will behave like a under reinforced section. So in under reinforced section, we know that concrete strength will not play a major role in improving the moment resistance, right? So we have discussed that in the moment curvature analysis. So what I'm trying to tell here is the bending resistance comes only from reinforcement. Concrete, especially in a column, pure bending resistance. So if we want to increase the bending moment capacity of a column cross section, we should increase the amount of steel that is provided in the column, right? So again, see, these bars can be arranged either in the square or rectangular or circular shape depending upon the cross section that you are dealing with, right? So let's see now, to find out what is the load that we need to take for column design. For example, if you see this column, an interior column which is connected by beams which are supporting the slabs above. For example, you have B1 beams which are running along the x direction, and then B2 beam that is running along y direction. Now, because they are connected to this column, the reaction from these beams B1 and B2 will get transferred to the column as an axial compression. So for example, if you take free body diagram of B1, let's say this is a reaction that you're getting. Similarly, if I take the free body diagram of a B2, which is part of the moment resting frame, and then if I do analysis and if I calculate this reaction, then if I take that as RB2, both of them will get transferred. So the total axial compression that is getting applied on this column C2 is basically PU is going to be RB1 plus RB2. 2. So this is the axial compression that is getting transferred to this column. In addition to that, you will also have bending moment about both axes. Here we are talking about only the axial compression. Now let us see how the load gets increased. For example, this is a G plus 2 structure. So you have footing here, and this is a ground floor. Okay, this is, let's say, the definition is somewhat different. So here at the ground floor, we call that as a first floor, and then the next floor is second, and then finally you have a roof. So if I take the section here, then you will find that whatever the load that is coming from roof has to go to this column, and then the self weight of this column should be resisted by this particular cross section. So if I take the section here, the total load that is coming is from this roof and then the column weight. Similarly, if I take the section here, you will find that the load on this particular cross section is going to be load that is coming from roof. Okay, from basically what we can say is from, so basically let's say this is, let's say, P1, right? So then on this section it is going to be P1. So that's what they're saying, load coming from this P1 plus whatever that load, that additional load that is applied, whatever that external load that is getting applied here, that will also come when I'm taking this particular cross section. So this, let's say the load on this particular cross section, if I take this as P1, okay, which is basically coming from whatever that external loads that are here plus the self weight, which is this, okay, that is basically load from roof plus self weight, okay, that is P1, right? Now, if I look at this case, then whatever that external load that is there, which is designated as second floor here, that plus P1 plus whatever the self weight of this column will be your load that is acting on this particular cross section. Similarly, if you look at it on this particular cross section, then you will find that, let's say this, if I consider that as P2, then it is going to be P2 plus whatever the load that is here plus, okay, self weight of the column will be your load that is acting on this particular foundation. That is the total axial compression that this particular footing has to be designed for, right? So as you can see that progressively we are going for a lower floor, the load gets increased. For example, let's say this is called P3. So P3 is going to be higher than P2, which is going to be higher than P1. Okay. So, so the load on this section is going to be less compared to this and this, right? So the axial compression force is going to get cumulatively increasing and keep increasing as you go to the lower floors. Okay, so now let us see how many types of columns are there. Columns, you can have this kind of a tied column where these stirrups, okay, we call that in beams, we call them at stirrups. In columns, we call these as ties, okay, and these are basically your longitudinal bars, okay, these are your longitudinal bars, okay. So you can see here that ties are put at certain spacing and to keep the longitudinal bar in position, and also it is going to reduce the effective length of this longitudinal bar, and it will, if I put closer spacing of these ties, then the bar will not buckle, and also the ties are going to play a major important role of providing shear resistance to the columns. Then we have another type of column for circular columns. You must have seen in bridges or some in ground floor of buildings where for architectural regions, sometimes architectural regions, sometimes they go for this kind of a circular columns. Where circular columns can have this kind of a spiral reinforcement that goes like this in the spiral fashion. This is a continuous reinforcement. Or you can also have circular column with individual circular ties. That is also possible. Okay, but if you are having a spiral reinforcement, the confinement effect is going to be higher, which we will discuss in the next parts of the module. So these are very common in buildings, okay, which are square or rectangular columns are very common in building. And sometimes for architectural reasons, we also go for this kind of uh, circular sections. Circular sections are very efficient in axial compression. However, from bending resistance point of view, because we are providing at the farthest point from neutral axis, you have only, because of the shape, you are putting only very less amount of your longitudinal bars. So the circular sections are not efficient from bending resistance point of view. However, they are very efficient from resisting compression loads because it is going to have uniform confinement, which we will talk about it uh, in the coming modules. And then we have columns can be again also can have composite columns, where what we do is we embed these kind of steel sections, okay, uh, like this inside the concrete. Okay, we can also have this kind of steel tubes also can be encased within that. So you can see here that this kind of different types of possibilities are there. Okay, with this basically what we end up with is very high load resistances, and it is going to be much more efficient in terms of load resistance compared to this other column. So you can economize the uh, design. So that is the basic advantage of going for composite column and so on. And also the concrete is going to protect the steel section, and steel columns are susceptible under fire. They can buckle and their load resistance would be less. So if you are able to encase these steel sections in concrete, it is going to protect these steel members, and so you can come up with a more efficient design. Now, so there is another classification for columns. Based on the length. Okay, so they can be classified either as a short column or a slender column. Okay, that is divided as a short column or slender column based on what is called as an effective length. It is not the clear height of the column. We have to use this effective length to determine whether this column is a short column or slender column. In short column, the strength is actually governed by strength of the materials that we are using and the geometry of the cross section. That means what kind of concrete strength that we are using, and it will be governed by material failure. So that means either concrete is going to fail by reaching its ultimate strain, or the steel is going to yield. So you end up with a material failure in short columns. However, in slender columns, you get a lot of additional deflections, which we call that as lateral deflections. That lateral deflections will induce additional bending moment, and if you're not careful, it can undergo stability failure, where stability failure is not the material failure. The column, before even reaching their material strength, it can fail suddenly due to uh, the deformed configuration being unstable, and then it will lead to sudden failure. So this is one way of classifications, which we will discuss in the coming slides. Then we can also classify the columns based on how the loads are getting transferred. Either if the columns are having only axial compression force that are getting transferred, then we call them as concentrically loaded columns. That means there is no eccentricity of the load application. And then the second case is eccentrically loaded columns, where when you have an eccentrically loaded column, you will have both compression as well as bending. Now the bending can be about both axes. Okay, that is, we call that as biaxial bending. Okay, so this is way we classify. So we can classify based on the arrangement of the reinforcement as a tied column or a spiral column or as a composite column, or we can classify them based on the length, basically the effective length, whether as a short column or a slender column. And then we can also classify depending upon how the loads are getting transferred to the column, either as a concentrically loaded column or an eccentrically loaded column. Again, eccentrically loaded column is more common because always you will have some eccentricity. In fact, code also mandates the design engineers to consider some minimum eccentricity in the design of columns. Right. So this is what again in schematic form. If you have the load that is transferred exactly in the middle without any eccentricity, then we call them as concentric columns. If you have load that is getting transferred predominantly by eccentricity with respect to only one axis, then we call them as columns that are subjected to bending and axial compression. However, the bending is only about this. In this case, if you look at it, the bending is about only this axis because you have eccentricity with respect to only this axis. In this axis, if you look at it, it is along the axis, so there is no eccentricity. So you will have, again, uh, you can design them for a combined bending and compression. And in this case, you will find that the load is getting applied at an eccentricity of Ex and Ey with respect to both axes, right? So you will have bending about both the axes. So depending upon which axis that you are having, so basically if you look at this axis about this case, now my bending moment is going to be P times Ey. So let's say this is X. So Mx is going to be P times Ey. Similarly, My will be equal to which is about this. So this is my axis. So we always talk about moment about an axis. That means moment about an axis means you take the eccentricity which is perpendicular to that axis of bending. So here it is going to be P times Px. That is the moment that we are going to take. Now, a very important classification is to classify the column whether it is a short column or a slender column. So that is what is going to be a very important classification. According to the IS code, okay, a compression member may be classified as a short column if the slenderness ratios with respect to major principal axis, which is LEX by DX. Always in IS code definitions, the major principal axis is actually considered as an x-axis, or in other words, if I take this cross section, this is, let's say, is a larger depth, which is depth, let's say, which is larger than b. So this is, let's say, b. So whatever that axis that I'm taking, which is perpendicular to the longer dimension, that axis is what I'm going to call that as x-axis or a major axis of bending. Now this is considered as minor axis of bending. Here they call that as so the dimension here which is crossing that major axis they call that as dx. The dimension that is crossing that minor axis they call that as dy. Okay, that means this instead of b I have to use dy. Okay, here it is dx. So this is the way we define. Similarly, the effective length also about the axis that we are calculating the slenderness ratio we have to take. So we will talk about what is effective length. So you have slenderness ratio about, let's say, the major axis of bending. In this case, it is x. Then how you calculate is the effective length about the x-axis divided by the dimension which is crossing that major axis, which is dx. Similarly, the slenderness ratio is going to be Ley by dy about the minor axis. For in this case, the IS code defines that when this ratio Lex by dx and Leu by dv are both less than 12, then we can classify the column as a short column. Now you can have a situation where it the slenderness ratio may be less than 12 about one axis for the same column, but it can be higher than 12 for about the other axis. Then you have to consider the slenderness effects when the ratio becomes more than 12 for that particular. So the same column in one direction it can be a short column, in the other direction it can behave like a slender column. So that is the you have to be careful. Right. So actually, this definition is not actually correct, especially for people who practice steel structural design. It is not actually a correct definition, but IS code tries to keep it simple. So they have defined that in terms of effective length divided by the lateral dimensions. But actually, it is not suitable for non-rectangular and non-circular sections where the slenderness ratio is actually expressed in terms of radius of gyration, which is a sectional property, just like the breadth and depth, rather than using the lateral dimension d. Okay, this is the more correct definition for slenderness ratio. Right. So that's what the AC code does. The AC code says that the dividing line between the short columns and slender columns is actually defined by the ratio LE by R, where LE is your effective length, R is your radius of gyration. In fact, that number is taken as 34 for braced columns and 22 for unbraced columns. So that means when the column is, again, I'm introducing two more terminologies, which is braced and unbraced, which we will talk about that. What is braced and unbraced conditions? If your column is braced, then the limit for your slenderness ratio is 34, or in other words, LE by R is less than 34 for a column in a braced case will be considered as a short column. If it is more than 34, it will be considered as a slender column. But if the column is again unbraced, okay, then the LE by R ratio should be less than 22 to be considered as a short column. If it becomes more than 22 for an unbraced case, it has to be considered as a slender column. So let's talk about why this is important. Why should we consider the effect of slenderness? So I'm taking a very simple case of a column. So this is the column, okay, which is subjected to pin condition, which is hinged. Okay, so we know the boundary condition. Hinged means it can allow rotation, right? Now I'm applying this load, eccentric compression, at an eccentricity of E. If we start increasing the load, the column that what you have seen here, it is going to bend like this, right? And so you can see here that uh, the column is bending, and you have larger deflection at this point, which we call that as, let's say, delta, right? And this is the way the column is going to bend. And this is the column that is hinged. That means top and bottom. See, the top and bottom of the column are free to rotate, but however, they are not going to move with respect to each other. Okay, so such type of boundary condition is, we say that laterally restrained column. It is only, I am allowing only rotations at the top and bottom end. Now for this member, if I take the free body diagram of, let's say I'm taking a section at a distance of x, let's say this is your top, and if I take the section at x, and if I am considering this, so this is a free body diagram. Okay, so you know the load is P, and this is at a distance of E, right? Now you see here, this is going to be this, and at a distance of x, it is having, let's say, a deflection of small delta. So if I take this, the original point of movement from the point of application as y, now you can say that the y will be equal to eccentricity plus delta, because the column is also displaced by a delta at the section x, and the total eccentricity now has become y, which is the applied eccentricity E plus the delta. Okay, so if I take the free body diagram, now again this has to be in equilibrium. So I have to generate some axial compression to satisfy vertical force equilibrium. In addition to that, if I take at this point, I have to satisfy also the moment equilibrium. So what is the moment that will be applied at this particular cross section? You will have P multiplied by E plus delta. So the moment will be equal to P into E plus delta. So you see here, if the column has not deflected, then the delta will become 0. So at entire length along the column, you will have only bending moment of P into E. Now the column has actually deflected laterally by a magnitude of delta at the section we are considering. So the moment will be not just P into E, it is going to be P into E plus delta. So this additional delta, because of the deformed configuration of the element, it is going to produce additional bending moment when the column is deflecting laterally. Okay, so we can also express simple bending equation as ei into d square y by dx square, as the moment that is applied is p into y. If I call this e plus delta as y, at any distance or any section x, the total eccentricity is going to be y, so the moment is going to be p into y. So we know that e into ei into d square y by dx square is equal to minus mx, the bending moment at that particular section. So here the bending moment is p into y. So this is it, a simple second order differential equation, and you can solve for this differential equation, and depending upon the boundary condition that you have, then I can find an expression for my p that it is going to fail. So this is the equation for your critical buckling load, which is PC, which is a critical buckling load. Right? So now you can see that when you solve for this differential equation, you find the solution for your PC as n square pi square ei by L square. Now depending upon what kind of boundary condition that you have, the n value can be 1, 2 or 3. Right? For this case that what we are considering, at x is equal to 0 and at x is equal to L, we know that y will be equal to constant of just eccentricity. There is no additional delta, right? So you can use your boundary conditions to solve for this differential equation and find an expression for your PC. So that you work. So in this case, n is going to be equal to 1. So you can find that for a column that is pin pinned, which is restrained to move laterally, then we'll find that PC is equal to pi square EI by L square. Right? So that is it. So now, what is the implication of this? Okay. Now I'm taking up, let's say, this particular cross section. Let's say this column is having a, let's say, a cross section of this. Let's say you have 300 mm by 400 mm, and I have some steel. Okay, like this, and I putting some nominal um, stirrup also. So in this case, if you look at it, what we can, for a particular cross section, we'll talk about that. We for a given material properties like concrete strength and yield strength of steel, and for dimensions, I can do analysis and I can find out axial compression, bending moment, interaction diagram. So this is also called as PM, interaction diagram, which we will talk about how to do that. This is a cross section capacities that it can take under different combinations of axial compression and bending. We will talk about how to derive this PM interaction curve in the subsequent modules. But now, if you look at for a particular cross section for this column member, if this is your axial compression bending moment. Now, if you see, if this column, if let's say this length of the column, okay, if let's say if this length of the column is, I'm taking L is equal to, let's say, 3 meters. Okay. So if the column is 3 meters and you have a dimensions of 300 mm by 400 mm, which is quite um, uh, robust. And if you find that 3000 by 400 and 3000 by, in fact, in this case, your effective length will be equal to uh, same as your L that you have considered. For a hinged condition, your effective length will be equal to your L, which is your 3 meter. So if you divide that as per IS 456 also, you'll find that this column is actually short column because 3000 divided by major axis, let's say 400, you will find that it is going to be less than 12. So if I start increasing this P, okay, for let's say I'm taking only L is equal to 3 meter case and with a cross section of 300 mm by 400 mm. If I start increasing P from 0, and if I start plotting how much moment that I am applying, and moment at any cross section, now you see moment at this cross section is going to be P into E plus delta. Now I am considering a L is equal to 3 meter length column, and the moment is going to be just increasing. If theoretically if the delta is going to be 0, moment is going to be P into E. for the cross section that I'm considering in the middle, if the column is very short, then the delta is going to be very, very small, or it'll be nearly zero. So then theoretically, the applied bending moment at that cross section is going to be just P into E. But we know that even for a short column, you will have some delta. So if I include this delta, you will find that the bending moment is going to not follow this dashed line, and it is going to follow somewhat like this. So initially you will find that at this low levels of your axial compression, delta will be equal to 0. As I apply more and more axial compression, you will start getting some delta. So the moment will become slightly will increase, which is P into delta. Now this delta value will be very, very small for a short column. So this is the behavior of a short column. Delta will be very, very small. Now for same column, instead of L is equal to 3 meter, now I am going to take L is equal to, let's say, 10 meters, just for discussion. Now, same hinge column, the length has become 10 meters. 3.3 times I have increased the length of the column. Then for such a column, you will find that uh, the if I start plotting, if I start increasing your axial compression, initially this portion will be straight, very closed, and then it will become non-linear, and then it will become like this, and then it will fail. Now, this green color is actually the capacity curve. Okay, this we call that as a capacity curve under combinations of bending and axial compression. So for a column of L is equal to 10 meter, it is a moderately slender column. If I start increasing the axial compression, the load moment curve is not going to be linear. Initially, it will be linear, and as I apply more and more axial compression, now the column is moderately slender. Now the delta is going to increase. So the moment the delta increases, the curve becomes non-linear. Then you will have this kind of thing. As I go more and more axial compression, the section becomes non-linear, or the elastic modulus and flexural rigidity of the section is going to decrease. That will induce more delta. Now, when I have more delta, again more moment. So the section or the load moment curve is going to become highly non-linear as a function of applied axial compression. However, still this curve will become, and then it will still touch this point and lead to material failure, or in other words, either concrete can fail in compression or steel can yield before concrete fails in compression, but you will be having a material failure. As a design engineer, we always want to effectively utilize the material. So when we design the sections, we always want the sections at ultimate to reach material failure. It should not fail by buckling before reaching their material strength. Okay, so now let's say if I, instead of 10 meter, I'm going into another case, I'm increasing this to, let's say, 30 meters. So you can see that 30 meter means 30 into 10 to the power of 3 divided by 400. If you see, definitely the slenderness ratio as per IS 456 definition is going to be much larger than 12, and it will get into the realm of a very slender column. So such kind of cases, if you start again plotting the load versus moment curve, that means if I start increasing the load from 0 to high values, then you will find that the curve will become extremely nonlinear, and the slope is going to become infinity, or in other words, the slope between moment to axial compression will become infinity, or in other words, the axial compression will reach 0, so the slope will become negative. Okay, that will lead to stability failure, right? So we don't want to have this kind of a stability failure. We always want to have this material failure. Okay, so short column also it reached its material failure, this also. So the moment the load moment curve touches this green color, that means we are getting a material failure. But if you look at the last case, for a very slender case of a column of 30 meter tall column, the load moment curve became non-linear. But however, it could not go and touch this value. Before reaching this material failure, it failed. So this kind of failure is called as a stability failure. This is coming from the stability related to the deformed configuration, which leads to underutilization of the material strength of the column.